Thank you for coming to this session. So today we're going to look at observability. Does anybody know what is observability? Okay, so there is a distinct difference between monitoring and observability, and I'll just very quickly run through. Okay, so this is not very technical. It's sort of like a very high level overview of why is it needed and what are the issues that it solves. And sometimes the solution is actually worse than the problem. Okay, so this may be one of those cases. Right? So let's walk through this. Okay, so how do we get here? Does anybody know what is this chart? Does anybody know what is this chart? This is the microservices of Uber in 2019. In 2019. So imagine, right, just now I was in the lab over there, I was talking to one of the gentlemen, I can't remember if he's here. He was saying that he's managing 10 microservices, 10, and he's having problems. Okay, so how did we get here? That's the question, right? How did we get here? Okay, so it started out with a very simple idea. I started a company, I want to be competitive, right? So previously we developed product, you just listen to a product, or maybe you have listened to a product where we have iterative waterfall, right? So I'm talking about software development, iterative, right? You got 6 months life cycle, right? You do iterative waterfall, you do case study, whatever. So we want to be competitive. But in this internet age, everybody is, everybody is slam dunking you with new features, right? So you want to be agile. So then you change from waterfall to agile. Agile basically means that I'm flexible to reprioritize my features. So if I see a competitor has a feature that something that I'm building which is not so competitive, then I can reprioritize that. So agile is a way to be defensive as well as offensive. So I think that I've got a good feature that may actually be good, so I can actually reprioritize it and build it. Okay, so that's agile. So business process. Agile actually came from the software world, but I think the business community has really adopted it. Right? So the business people were churning out ideas, right? So very good. So then the software developers cannot keep up, because our old way of doing software is you got dev team, you got ops team, okay, and they don't talk to each other, right? So what do we do? So around about 2010, so there's this practice called DevOps. So no more walls between a developer and an operations person. Okay, the best person to deploy the application is the person who wrote it. Okay, so that's the mantra. So that's what DevOps is. So DevOps allows your development team to be able to develop application faster. But no point having to develop application faster if you cannot build it fast enough, right? Okay, so we adopt a third thing, the CI/CD. So this is where the third part of the trifecta comes in. So the CI/CD pipeline. So CI/CD pipeline allow me to build on demand, build manually, or build on schedule, or build when it's something trigger, right? So the stages of the pipeline. Anytime you push, we do integration, we build. Okay, so this happens. So the next thing that happens is this: our software is monolithic, right? So we are developing it, and we got lots of teams, lots of features. So it's very difficult to coordinate large piece of software to be delivered, to be built in a CI/CD pipeline. Okay? Not everybody works at the same pace. Not every team works at the same pace. Okay? So what we do is let's break them up and let's make every module a service by itself, or like a server by itself. Okay? So what we do is that we prioritize parallel development and independent deployment. So we break up our application so that they can be developed in parallel. All the modules can be developed in parallel, and they can be deployed and scaled independently. Okay? So around about 2015, or actually 2008, but 2008, 2009, but about 2012, 2013, 2014, that is where cloud began to take off. Okay? So management sees an opportunity to reduce OPEX and CAPEX. Okay? So I don't have to upfront buy all my hardware, right? So just rent it first, right? You'll be all right. Okay? So we adopt cloud. But remember, previously our application was just one big monolithic, very simple. I just get a server, run. Now I've just broken them up into hundreds of small pieces, right? So one server, one module for every server is not feasible. Even if you're running on a cloud, it's not feasible. Okay, so we need a new tool. So around about that time, a tool actually emerged, a platform actually emerged, which is called containers. So containers are essentially very, very lightweight, isolated processes. Okay, so they behave like a server, but it's a server within a server. So you can, from one server, you can have many, many containers isolated in a server. Okay, so we've got that. So now all of this can run very cheaply on containers. But containers are like little kids in a room. How many of you have ever been to chaperone, birthday kids for your nephews, 5 years old, right? They say, okay, let's play a game. Nobody listens to you, right? So containers are like little kids without supervision. So we need to control them. So how do we control them? We use a container orchestration platform like Kubernetes. So that is how we got this picture. You all started by being competitive. So now, this guy says, now we replace all our monolith with microservices so that every application now looks like a murder mystery. Because previously, if a thing breaks down, I know in this application it breaks down. But now when it breaks down, I do not know where, because it could be in the entire request trace. Okay? So essentially what we do is this, we trade operational simplicity. Previously, monolithic were very, very easy to operate. So we traded operational simplicity for business efficiency. Okay, we want our business to be efficient, so we traded that for operational simplicity. Okay, so complexity doesn't go away, it just gets shifted to somewhere else. It's somebody else's problem now. Okay? So, but having said that, cloud native, so this type of application, which I'll call cloud native, okay? So cloud native application has its merits, okay? First of all, they are immutable. Unlike our server, if you ever install server, I've actually been in support for a very long time before I joined this, right? Before I become a lecturer. Sometimes, we will say, it works on my computer. Yeah, but we are not shipping your computer, right? We're shipping that server, right? Okay, because why? The configuration is different, see? So, but with those type of things I've shown you in containers, they're immutable. That means every single one of them is the same. So I can virtually guarantee that if one of them runs, everyone will run. So it makes automation very, very simple. Okay? Secondly, cloud native applications are ephemeral. They are dynamic nature. I can scale them up and scale them down. With physical servers, I cannot scale them up and scale them down. But in Kubernetes, with one command, I can scale up the server. Of course, provided you have the CPU and the resources, I could just scale down with one single server, right? So it can respond to dynamic demands and conditions very, very easily, traffic conditions very easily. The third one is idempotent. You cannot, most of these systems, you cannot apply. Generally, sometimes, when we, in physical systems, when we apply some configuration and we apply again, the new configuration may override the old one, or you may run into problems. In cloud native system, there's this property called idempotent. In other words, if I've applied once and applied the second time will not have effect. The example is, if I delete a file, and you delete it again, the file is deleted. The second time you do, it's still deleted. That's called an idempotent property, and it's very, very important because a lot of configurations come from people reapplying configurations again and causing issues. Okay, so these are the 3 properties of cloud native application. This is their strength. Okay, so we mentioned that the cloud native applications are immutable, they're ephemeral because I can move them around, and they're idempotent, right? So to handle this kind of availability strategy, so in other words, right, in a microservice environment, right, the applications can actually go off and go on very dynamically. So to handle the availability, service availability, right? So there's a few standard strategies that we adopt. The first is the standby and replication strategy, right? So very easy. You got hot standby, cold standby, databases, right? You replicate your data, okay? Second one is load balancing and auto-scaling. Request comes in, depending on what sort of load balancing strategy, I just direct that, okay? Right? And also, if I detect that all my instances in a cluster are sort of almost full, I could spin up new instances, okay, to handle the demand. Okay, this strategy, auto-scaling, is maintaining SLA. So I've agreed to certain SLA to my customer, right? With 4 instances, so I said, 50 requests per second, right? But now I've hit the 50 requests per second, but still requests are coming in, right? So I need to maintain my SLA. I cannot let it drop. So I spin up more. So the third one, of course, is circuit breaker. Circuit breaker prevents cascading failure. So remember, microservices is just essentially a series of distributed applications that are making call to each other. So imagine if one of them in the middle fails, right? You'd have this chain effect, right? So the first one, it fails, it has a chain effect, it doesn't matter. But the second one, the second time when I call it, I know that it has failed, right? So I shouldn't spend my time, just going there. It's like the first person doesn't know, you're driving down PIE, right? There's a road, there's a traffic jam, right? So then I spend 1 hour there. So I go, and then I come back again, right? I already know that there is a traffic jam, right? So I avoid that. So that's what circuit breaker does. It allows you to avoid that mistake, that congestion, that area. The third one, of course, is, the fourth one, of course, is rate limiting. Not all services are written the same way. Some are written in Python, Golang, whatever. So certain applications, certain runtimes have better throughput, is able to handle more throughput. So rate limiting allows a consistent service. Even sometimes, last time previously I was working, even if an application can handle very high throughput, we will want to temper expectation. That means we do not want to show hand too fast, we do not want to serve too fast. Okay, so you want to do that. And then finally, service discovery. When new services come up, we want to be able to, not to code in IP address, but to just find them by name. Okay, so these are the strategies. So all these strategies, right, are essentially just preventing a system from failure. So have you watched Toy Story, the first one? You know where is this scene? It's chasing a truck, right? Remember what Buzz said to Woody? Woody said, "Hey, you are flying." You know what Buzz said to Woody?
Falling with style.
This is falling with style. So essentially, all these strategies are just basically failing with style. You're failing, but you're failing it in a graceful manner. Correct? You're failing, right? You're failing in a graceful manner. Okay? So these availability strategies, right, just keep your system up. They don't address the failure. Okay? So we limp along, like, let's say I need to give a presentation today, I've got a headache. So what do? I just take a Panadol. That's my resiliency strategy. Right? So it doesn't address that, right? It just makes sure that I can deliver the work. So that's the idea. So we stave off failure until such time that we can have time to look at it. But so let's switch gear a little bit. So this ability to adapt and ability to rapidly adapt to disruption, this is resiliency, right? So in other words, in a very simple terms, it just basically means service uptime. I just want to keep my service uptime. Okay? So if we focus very narrowly on digital services. So resilience is not about preventing failure. In microservices, in such distributed system, failure is expected. You cannot prevent it. Okay? Right? So, but what we want to do is that we want to adapt when failure occurs. And typically in microservices and in distributed environment, right, you don't get total failure. Total failure is easy to handle. Everything fails, I know. No problem. I can fix it. It's partial failure. Okay? If you got a car, right, you're driving a car, right? If your car breaks down and stop, very easy. Just tow truck, pull to mechanic, right? You know what's the problem? Is when you drive, there's a sound in the wheel. But you don't know what it is. That's the one that takes the longest to fix. That's what partial failures are. Okay? So we want our resilient to be able to absorb these disruptions, maintain service, albeit at a degraded level. So you must temper your expectation a little bit. You must say, yes, I can limp along, but I should also expect degraded performance level or service level. Okay. The goal here, the goal of this resiliency, is to really to improve the mean time between detection. I want to be able to detect errors faster. I also want to be able to recover faster. Those are the two main goals. Okay. So today our tools, right, are essentially from the early 2000. Okay, our CI/CD tools, right, they are essentially for single server, fairly static environment. Okay, so in a distributed environment, right, when an error occurs, okay, it is because of the interaction and some concurrent event that has occurred, that has surfaced this bug. And this event that you see may never happen again in the next 1,000 years. So your bug never surfaced. Okay? So typically what you do is that if you have this problem, what you do is you call support, right? You know what's the first thing that support asks you to do? Is it reproducible? That's the first thing they ask. Show me how to reproduce it. Then I can fix it. Okay? But typically in a lot of these distributed systems, it is impossible to reproduce. It is impossible to reproduce. Okay? So, which brings us to the traditional monitoring approach. In a traditional monitoring, right, you know exactly what is going to fail, so you're going to look at it. So for example, if I got 1 or 2 servers, I set up a monitor and I look at it, right? But in microservices, right, it's more than just an application. So one of the big difference between when you're writing a microservice and a traditional monolithic application is this, right? So I'm actually a software developer. I came from, C++, and Java. When we write monolithic application at that time, our applications are written not to fail, first of all. Secondly, it's written to recover from error. Okay, we got try catch, we try to recover from error. Okay, today a lot of microservices, right? The mantra is fail fast. If you got a failure, don't recover, just fail. Because it's easier to restart, okay? So Windows has been doing that successfully for the last 50 years. Okay, anything wrong with Windows, just reboot. Don't forget about recovery. Okay? Okay? Linux will recover, we'll try and recover with Linux. Yeah? No, don't. Originally I laughed because I used to work for Sun Microsystems and then Oracle. And then we used to at Windows, right? But if you think about it, it's actually a very sound strategy. Why spend so much time trying to figure out all the different ways that you can fail when just reboot? It's a good strategy. Okay? So now I'm older and hopefully a bit wiser. So typically what we do is that we will monitor CPU memories, right? But in microservices, right, it's not about this. Okay? Typically, if you're out of memory, for example, the containers will just restart for you again. It's not, that's not an issue. Okay? The issue is the interaction. Microservices is about interaction between services. You want to capture that. Okay? And you want to be able to reproduce and understand this in interaction. So if you want resiliency, you cannot improve resiliency if you do not understand how the system behaves when it's under stress. When certain parts of it break, you cannot have resiliency. So you need to understand your system. So the more complex interaction, the more you need to understand. Right? So this is where observability comes in. So in observability, typically we do monitoring. So we only monitor what is called metrics. Right? Like CPU utilization, bandwidth, right? Requests per second, right? But in observability, there are 3 things that that typically we try to capture. The first is metrics, of course. The second are logs. So a lot of applications are writing logs. The third one is traces, because these 2 things doesn't tell you where the request goes. It's the third one that tells you where the request goes, the trace. I'll show you an example of it afterwards. So these three things. So these three are called the three pillars of observability. Okay? But it's no point having them individually like this. You need to be able to correlate them. To say that this particular matrix or this matrix, this latency matrix, this P99, 5-second P99, my 99 percentile latency at 5 seconds, right? So that's my matrix. What caused it? Where is the trace that caused this, right? And at that time, what is happening? You must be able to jump from that, okay? So the important thing is not only to have this, but also to be able to correlate them. So in observability terminology, there's this thing called an exemplar. Exemplar is essentially just a data point that links signals together. Okay? So, very simply, I won't go too much into it. The way we capture, so if you want to do this, the way we capture this instrumentation is you need to have an instrumented application. So in other words, you need to have an application. Oops. What happened? Did you switch something? Because I just lost. I just lost my screen over here. Sorry. Settings. Oh, mirror. Okay. I don't know why it's soft. Just okay. Sorry. So you need to instrument our application. So by instrumenting our application, what I really mean here is you need to put code into your application that generates logs, of course, traces, and metrics. Okay, and then all that is sent to a collector in the middle. So this collector can do things like hydrating and enriching and do cross-referencing of your signals. And then after that, they are sent to the backend. So backends, your common backends are like your Grafana, your Prometheus, your Loki, etc. You may also, if you want to do study long-term, you may also want to store them on long-term storage, either using Thanos or Mimir. And then finally, you have a dashboard like Grafana that monitors them. So this is architecture. So typically today, all of us will just send directly to this, and then you send to this. Okay? Then you miss the part where there's correlation. Okay. So if you have metrics, right, and you want to capture your metrics, okay, what is it that you want to capture? Okay. So these are four basic signals that you can capture. So the first of all is latency. Latency, that means when a request comes in, how long do I take to process it? That's latency. Okay? The second one is traffic. Traffic is how much request is coming in. Right? So that's traffic. The third one is errors. How much error am I generating? My application is generating, right? The fourth one is saturation. How saturated are my servers? That means how busy are my servers running the application. Okay? So this is Google's 4 golden signals, SRE. Okay? But these 4 signals can actually be arranged into 2 groups. Okay? So if you are interested in monitoring your resources that means your database server, your CPU, your disk. Okay? You use the metrics, you use the use metrics. Use metrics stand for utilization, how much utilization is happening on your server, how saturated they are, and how much error you're producing. If you want user experience, customer experience, okay, then rate. Rate is request, how many requests coming in, that means how busy is my service or how busy is my website. Okay, how much error am I generating, and how long do I take to process each request. That's a rate metric. Okay, so these 4 can be grouped into these 2 groups, and they focus on different things. Okay, so now, so I've talked about half an hour, so I'm just going to very quickly do a demo. Okay, so this is the OpenTelemetry demo. You can actually go and download it and run it. There are two ways to deploy it. You can either deploy it with Docker, using Docker Compose, or Kubernetes. This one has about 15 over services written using all different languages. Okay. So I won't really run into this. So this is the application itself. I mean, it's just fairly simple, you know, my telescope and stuff like that. Okay. So okay, I've got demo script here. Okay. So so this is the Grafana that's running, and based on the request, because I've got load generator that's sort of generating the request. So based on the request, right, Grafana is able to track how the architecture is. So this arc here, this is the number of requests. It's some weight. Basically, just means that how heavy is this piece of thing? How heavy means how much traffic is going through this. It's just a number to show the weight, how important this is, right? Okay. So it looks like all of them is coming through this central proxy, and so it goes down here, right? So let's do this one. So I can center on here. Sorry, my screen is very small. If you're interested, across the side there's this Apollo demo room, right? They've got a bigger screen, so I can walk you through that a little bit more. So this is the front end. Okay, this is the front center here, right? Okay, so let's look at something. Let's look at this checkout, and let's look at the traces for this. So remember the trace, right? So we click on this one. We can see the trace. There's a lot of error because I've actually forced the error. Okay, so the error is failing. Okay, so you can see a lot of error. You can see how this thing workup is. So these are the services. Okay, so for this one there are 2 upstream, and it goes down to 4 of this. Okay, so I can click into this one, right, and see actually what is happening, right? So if I click into one of these things, so this entire thing is called a trace. A trace basically means a request comes in, it goes through all the services, and then it returns. That's a trace. Okay? Now every stop it makes, okay, it's called a span. Okay? It's called a span. So these are spans. So it comes in through here, it goes through here. So you notice that it's hierarchical. So you know the order, right? And we don't really see a lot here. So in this case, because it's too dark, so we can actually look at this one. Okay, we can actually look at this one. So we can see, in this case, we can look at the graph. This is the graph of the call. Let me just zoom in a little bit for you. So it's just showing you, how the calls are, right? So it's telling me that this particular request takes this much time, and it went through 4 services. The 4 services are the color. So why are some of them the same color? The same color means that they are inside the same service. So we are creating spans, or what you call internal spans, inside the application. Okay, so that's the reason. Second one we can very quickly look at is actually the flame graph. Okay, so this one flame graph just tell you, where is the time being set. In this case, it is not an issue. So this one spending 63 milliseconds on itself, because sometimes the total is the cumulative of all my spans, including this, right? Okay. Let's go back to this one. So let's look at this one again. So we can find out actually what's the error. So we can click on this one, find out what's the error. We click on this one, it expands this. Again, all this you have to capture it. So we have got a log here, and so if you look at the log, okay, by the way, this is a contrived example because I know what's the error, right? So that's why I'm pinpointing to it, right? Okay. So it's saying that there's an error in the lookup. So the DNS is having a problem. Yeah. Okay. So this is just the trace. Okay. So typically it's what you do, right? So what observability allows you to do is this. So remember, this is our entire system, right? Observability allows you to ask questions about the entire system, things that you haven't even thought about. Okay? Treat this whole thing as a system. So you cannot do this with Jaeger. This is Jaeger. You cannot do it with Jaeger because Jaeger is only focused on traces. Okay, so to that, we need to switch over to Grafana. Okay, so this is the Grafana. Okay, so this is the Grafana dashboard. Grafana is sort of like a universal tool, and currently I have got the following data source configured. So I've got Jaeger, which is just now that one. I've got Loki. Loki is logs. I'm not using OpenSearch. Prometheus is metrics, and then Tempo is the trace, okay? So let's do that again. Let's use Grafana. So let's assume that I don't have the Jaeger tool, and I now want to find that request just now, okay? So I can go to Explore. Okay, so I can go to Explore, and I can select, I want Tempo. This is my trace. So I can say, remember just now it's checkout, right? So I can say resource, service name, checkout, okay? Give me, sorry. So this one means find any span. The first is a trace. Find any span. Status is error. Okay. So it now returns the error. So same thing. So if I click on this one, I'm going to close this. We will see the same thing again. See that? It's the same trace, right? But now this is more. So if I click on this guy, right? So this is the same error, right? But because I've got exemplar in here, I can click on this, and it will go to the log, and it will tell me what is the error. Jaeger cannot do that. Okay? So this one I'm able to jump to the log. Okay? So one more example. Okay, one more example. So we go to dashboard, and I'm going to look at this exemplars. Okay. So in this case, this is a matrix. In this case, this matrix is a Prometheus matrix, and what essentially we are doing is we are just basically. So don't worry about this one. We are just basically calculating the rate of this get cut something. Okay, so don't worry, just get cut something. But because this matrix, right, is a continuous metric. Continuous metric, that means it's a continuous number, it's a real number, rather than this discrete matrix, a single value. So to count it, you cannot count real numbers. So the only way to do it is to bucket it. It means to use a histogram to bucket it, right? Okay. So this is the bucket. This is the bucket. Okay. So this is a flame graph or heat map. This is a bucket, and these are the time. See that? Okay. So each one of these, right? So remember, this is the metric, right? Each one of this, this thing is a correlation to a trace that produces this matrix. Okay. So I'm going to move out a bit. I'm going to click on. Let's click on the, because I don't storage, so I need to click on the later one. So I click on this one. Too small. Let me make it smaller. Okay. So like this. I'll click on this guy. Oops. Okay. It's not very difficult to. I cannot click it because my screen is too small. Let's try this again. Let's see whether I can click it. Come on, let me click. Why can't I click? Let me reset this. Sorry. Okay, let's try this again. Okay, let me go out and come back in again. So there's a problem if you have a very small screen.
Or you can zoom to 50%.
Where is it? Here? No.
Just now,
Where is it?
browser has a 100%.
Yeah. The problem is that it cannot.
Oh,
The scale. There's a bug with the code, so there's a scale. Okay? So yeah, the scale is wrong. The scale is wrong. So let me just try this again one more time. I want to show this. Oh, I still got. What is that? Change the time frame, make it smaller. Last 5 minutes. That's a good idea. Let's click on this guy. See? Okay. So the problem is this. I cannot. See? Because my screen is too small. It's actually down here. So this one, if I click on this thing below here, you have to trust me on this. So it now jumps to the trace. So it's that trace that produces this thing. So we go from metrics to trace. Okay? So see this line here, this is called critical path. This is where it's executing. So we can look at this one. So we click on this one. Now we jump to the log. So this one don't have the log. So it depends on whether a log is captured, whether there's a log in it or not. It's up this application, right? So but in this case, this one do not have a log. So notice how, using exemplars, we link the 3 signals together. Okay? So let me go back to here. Okay. So the question at everybody's mind is this, what about AI? Okay? So Grafana has an MCP. Okay? So you can create a service account and then you can configure MCP. Right? So what I'm going to do is this. So this is one of the applications that I've deployed. I've got some prompt, right? I need to, because I've tested it quite a long time. Okay. So this is one of the applications, and it's got a metrics, and it's this specific metric. Okay, so the metric name is called quotes total. Okay, quotes total, right? So let's do something first. So I'm going to use Claude Code. Instead of seeing me hit, enter all the time, what I'm going to do is I'm going to do something. Don't try this at home, boys and girls. Okay, that means it's just going to execute it. It's not going to ask me anything. Okay, so I'm just going to check if my MCP is connected. So Grafana is connected. Okay, I can list the tools. So these are tools I can create incident in Grafana and stuff like that. Make sure you need to create a service account for this for people to access this. Okay, so I could say something like this. Let me put my code. Okay, look at Grafana and let me know the use, remember use, metrics of the server running the application. So I'm asking it, right? Remember there is no use metrics on the dashboard. So it's now go and, so you got to wait about a minute. So it's now going to run some, so it's going to check out what are the data sources I have. So I've got Prometheus. Then it's going to create Prometheus query to try to find out the utilization of the, see, notice it's found Prometheus data source. Because if you don't have Prometheus, it cannot query. It will go and try and find other ways to query. Okay, but it's got Prometheus, so it's just going to use the most direct way to query. Okay. So it's still going. So it's going for all the utilization. Use is utilization, saturation, and error. So it's going to do all that. So we'll do, after this, we'll do one last one. Okay. So that is my use metrics for my server. Okay? So let's do another one, okay? So remember this application, I've got this metric, right? This Prometheus matrix, okay? So let's ask it to create a dashboard for this matrix, okay? So create a dashboard to track the rate of codes total. Let me get the name correct. Is it codes total metric. Okay, so it's now, so this is the original Grafana. Let me go back to the, okay, let it run first, okay? And then I'm going to go back to dashboard. So now it's going to look at my source code, look at the metrics, and then it's going to try and create the metrics. So it's found the metrics in my source code. Yesterday I tried once, it sort of got an error, but after I tried a few more times, no more error. So hopefully, you know. Okay, so now it has created the metrics. So let's go and look at this one. We refresh. And hopefully, there we are. That's our metrics. And that's the metrics that's created. Okay? Right? So one other thing, I'm going to let it run first. And then after that, we'll come back to this, right? Create a metric to, so what I'm going to do is this, I'm going to try, this is totally unscripted, okay? So to track the rate, the latency for this request, okay? Create a metric to track the latency of slash what? Slash code handler. Okay? Do not create the dashboard. Just insert, just use the OTel, Open Telemetry, JavaScript SDK. So I'm going to let it run for a while. We'll come back to it after to see what happens. Okay? Right, okay. So resilience to observability. So we've got this loop. First of all, you need to instrument your application. Okay, we need to put code, we need to instrument application, and then you observe what is happening. Okay, and then you experiment. So it's very important that you experiment because you need to introduce. So I know this is a very novel concept, right? Normally production system, we try to keep it running, right? But in distributed systems, you want to disrupt it, and you want to control the disruption. It's called chaos engineering. Okay? Because if you don't disrupt it, you will never know how the system behaves. Okay? You don't want to find out when there's a real outage. You know what I'm saying? Right? So you want to perform experiment, and then finally, to see whether and then you adapt to this. Okay? So essentially, a resilient organization, you're trying to build a resilient organization is, you build your organization for recovery, not for perfection. Okay, you expect things to fail, so when they fail, don't scream at your, at those reporting to you, because it will fail. Okay? That who has no seen cast the first stone, that type of thing, right? Okay? So expect system to fail. Okay? So So trust in the capability of your people. You give them tools, okay? Very important. Giving tools is not enough. You need to train. The second thing, people train. The second thing people don't do is what? No, drill. They never drill. You need to drill. Okay? You need to drill. Right? No point having a backup if you haven't restored it. The backup is as good as don't do any backup. Okay? So third thing, and very important also, I find is, because I do support, so you know, the support, nobody likes to do support job, because support, right, if you go down to support customer side, right, you know, everybody is in a foul mode. Correct? That's support. Right? And sometimes I go in there, people are not behaving rationally. Okay? So you need to behave rationally. Okay, so I've been in support for quite a long time. Okay, so I'm telling you this from experience. Okay? Learn from outages. Every outage is unique. Do you know Anna Karenina? The book by Leo Tolstoy? Okay? Okay, doesn't matter if you don't read it, doesn't matter. Go and read the first line of the first chapter. The first chapter says this. Happy families are all alike. Every unhappy family is unhappy in its own way. So essentially what it says is this. Okay? Every successful software, or every happy family, they are all happy for the same reason. Okay? Every unhappy family is unhappy because of their own unique reason. So, every system that is successful because of the same reason. So you can learn from that. But also, every outage is unique. You should also learn from that. Okay? Set clear objectives. Okay, if you're in the service sector, set clear objectives. Typically for us, it's not SLA. SLA is what my boss promised the customer. SLO is what we do. This is the objective, and SLI is the numerical value that we track. Okay, so how much can we afford? How much can we afford downtime this month? How much more? Then everybody will be on their toes. Because if you do not know that, then nobody has any urgency. Okay, and that change and evolve. So use control disruption. We've got processes, right? We think this happens, so this is how we're going to behave, right? But when you use chaos engineering, or when you control disruption, you break down things, then you find that your assumptions are incorrect, or you may find that assumptions are incorrect. So at that time, you need to re-architect a system, retrain, reskill the personnel. Maybe they don't have this kind of skills, and then redefine your processes on how to handle them. Okay, so. Basically, essentially, this is just a part of the whole, this one. There's actually a lot more, which I'm not going to talk about, which I've run out of time. I've got courses. You can get this slide and you can have a look at it. Okay, I won't go to, it's just not DevOps, it's just not observability, it's DevOps security and stuff like that. Okay, so you can go and have a look at it. Thank you.